Okay, so in the definition of integrals, we always concede an interval, a finite interval. Okay, it's interval from A to B. Okay, and the integral is going to be the limit of the Riemann sums, right? Now, when we write on the Riemann sum, it's always a finite sum of. You divide the interval into many subintervals, and you pick up the points in subinterval and you find the value of the function, and you do the, this is a, and then you add them together, then you get a Riemann sum, and then take the limit, right? So the integral originally is defined for the function defined on the closed interval, bounded closed interval. So what happens if the function, and the function is defined everywhere, okay? So this is a, yeah, so if the, we recall the definition, right? So if f is defined on a closed interval, that means it's defined everywhere. Then the integral of this function is defined to be the Riemann sum, right? And here's f of xi star and delta xi. Okay, as long as all the delta xi goes to approaches 0. This is a, yeah, I should put it in the limit. Okay, and that's the definition of the integral. So the function must be defined at every point, number one, and the interval must be a finite, a bounded closed interval, cannot be open. So what happens if the interval is not bounded, or if it's not closed? Okay, how to define the definite integral? So if the interval is going to be something like that, okay, then how do you define? Yeah, I should say if the function defined on the, if f is defined on the interval, something like that, it's not finite, then the integral of this function is defined to be the limit as b approaches infinity and from A to B. Okay, so first of all, you have to evaluate the integral on the finite interval, and then you let b go to infinity. Okay, so the definition is very simple. Similarly, if f is defined on an open interval, okay. Now this time, the function is not defined at point B. It maybe can be defined, maybe not, right? So you cannot use a Riemann sum to define because f of b is not defined. So you still have to use the definition. Let's call, let's say t. T approaches b from negative side, and this is a to t, and f of x dx. Right. So at least the function is defined from a to t for any t less than b, a closed interval. Right. Yeah, here's a note, right? F is defined on any of this interval for any t greater than a less than b, okay? So it's closed. That's why you can talk about the definite integral, okay? Yeah, in the definition of the integral, the function must be defined on a bounded closed interval, right? And the function, and the integral exists when the function is continuous freely. Okay, so if the function is not defined at the one end point, you have to take a limit of the integrals. That's all we needed to know for today's class, and let's do some exercise. Yeah. So let's evaluate the integral of the following. Okay. The typical one is integral from 1 to infinity and xp dx. How about like that? And here p is greater than 0. I want to see when or whether this is going to be, what is the value of that? And what is the geometry meaning of it even, right? So first of all, this is going to be the definite is going to be integral from 1 to b of x of p dx. Okay. Right. So now you have to find the antiderivative of the function. So this will be x to the negative p. So antiderivative of the function is going to be 1 over 1 minus p, x to the 1 over minus, right? Now be careful. I have to say p when p is not equal to 1. Otherwise, this cannot be used. Okay, so when p minus 1 is not going to be 0. Okay, if p equals 1, that will be different story. Okay, and so we get this. I got 1 minus p and b 1 minus p and minus 1 minus p. Okay, right? When x equals 1 to any number is equal. Okay. So the question is when this limit exists. I think it have two possibilities here. If p is greater than 1, this can be 0. Okay. If p is less than 1, 1 minus p is positive. So this can be positive infinity if p is greater than 0, less than 1. Okay. Now what happens when p equals 1? When p equals 1, if p minus 1 equals 0, right? That is another case I have to discuss. Then I find out the antiderivative of this function will be nature log of absolute of x, which is difference at 2 endpoints. That will be nature log of b minus nature log of 1, which is 0, right? Nature log of b minus nature log of 1. And clearly this can be positive infinity because when b goes to infinity, and nature log of b goes to infinity. Okay? So now we conclude that if p is less than or equal to 1, it is infinity. If p is greater than 1, it is convergent to, wait a minute, there is a minus 1 minus p here. Okay, I'm missing that part. Okay. So when p is greater than 1, this is 1 over p minus 1. Okay, so let's conclude the following. Okay, first of all, this is infinity. If p is less than or equal to 1, then when p is greater than 1, I got 1 over p minus 1. This is a positive number, okay? Yeah. Now, what is the geometry meaning of this? The geometry meaning. The geometry meaning of this. Okay. So first of all, let's still go back to the limit. Okay. So the integral from 1 to b is going to be the area. Okay. The function is always decrease. Okay. This is y equals 1 over xp. If p is greater than 0, it's also going down. Okay. And this is a b. So this will be the area of that region. Yes. So the area is going to be integral from 1 to b. right? So if we let the b go to infinity, and the limit should be the area of the region under that curve. Now the size of the region is unbounded, okay? Because it's never end. It's going to positive infinity, and of course the gap is getting smaller and smaller, okay? But the size, this is still very long side, you know, okay? So, but the area could be finite, okay? So that means if p greater than 1, the area under the graph y equals 1 of xp is going to be 1 over p minus 1, right? So it's a finite, right? You have finite area, although the region is unbounded, okay? Which is going to be the area. Now, yeah. Yeah, although the region is unbounded, but the area is still finite. It's possible, okay? And if p is greater than 1, 1 over xp decays very fast. So it closes the gap very fast. Okay, every step further, you gain a less, very tiny small area additional. So add them together, it's still finite. Okay, so we are going to study the sequence in the future series, and you will see that. Yeah, you will see that you're getting more and more terms added to the sum, but each time the addition term is so small and decays to 0 so fast, so you are not going to get the infinite the value. So it's still finite. Okay, for this particular problem, the limit of the areas is going to be the areas of the whole region. Okay, and there's a graph, and which is going to be 1 over p minus 1 if p is greater than 1. If p is less than or equal to 1, then it's going to be 0. No, it's infinity, yeah. If p is between 0 and 1, 1 over xp still decays to 0, but it's at a slower rate. So it includes an infinite area. Okay. This is a typical example. We will use it over and over again. Okay. My next problem is look at the integral from 0 to 1 natural log of x dx. Now, why this is the improper integral? Now, look at the function. Right, this is a function, y equals natural log of x. So you know the problem here. Okay, so the function is not defined at its origin. Okay, is defined on the interval from 0 to positive infinity, but does not include 0. Right, cannot be defined. So the integral from 0 to 1 should be understood to be the limit of integral from positive epsilon to 1. Okay, so this one should be understood as epsilon greater. Okay. Right, and epsilon approaches 0 from positive side. Epsilon is positive, so positive epsilon to 1 is a closed interval. Okay, so this is a natural log of x is defined on epsilon 1 for any epsilon greater than 0, less than 1, right? So therefore, this integral makes sense. The integral of natural log of x from epsilon to 1. So let's find the antiderivative of this. We antiderivative the natural log of x. I think we already get something right before. Okay, so this is going to be x times 1 over x dx. So answer will be, because this is the antiderivative of the natural log x. You know, I forgot the answer, so I have to derive it. I cannot memorize all the stuff. Especially when you're getting old, that's right. You know, sometimes you decide to go shopping. You write down 6 items on a piece of paper. But when you get to the supermarket, you find, where's my paper? It's on the dining table. That happened. Okay. Yeah, it's biological, you know, the biological brain. The brain is biological. So it can easily lose some data. Okay. Well, the computers, of course, is also crashed, you know, some bad cells, right? You cannot. Yeah, I think these days the computer hard disk drive is getting better. I usually, when I have 10 years ago, you know, I always have some problems with my computer. These days, I don't have much problems, right? Yeah. Have you had any bad experience with the computers crashing down, right? Unless there's some virus getting in. Yeah. All right. So let's look at. So this is going to be integral, right? From 0 to 1, from epsilon to 1. So x, natural log x minus x. Okay. So that is going to be 1 times natural log 1 minus 1 minus epsilon natural epsilon minus epsilon. Okay, so what is the 1? Natural log 1 is 0, so it's negative 1. Minus epsilon natural epsilon plus epsilon. Okay, when the epsilon approaches 0, the only problem is this one, right? So you have to think about, yeah, the limit. So I forgot the limit. The limit epsilon approaches 0 from positive side. Okay. So I want to see whether epsilon times nat that's right. It is going to be 0 or not. Okay. So we have to look at this. Okay. Again, there's another problem here, right? I have to find the limit of this. When epsilon approaches 0, I can do the following. Okay, this is I have to apply the L'Hopital's rule to solve the problem. So I'm going to you have to write as a quotient. So it's better to write in this way. Okay, so this will be infinite over infinite type. Then you can apply the formula. And you will get 1 over epsilon, the derivative, is 1 over epsilon squared. So if you simplify, you get negative epsilon, which is going to be 0. All right, so this part is going to be 0. Then you can go back to here, it's going to be negative 1. Okay, because the second one, the limit is 0, the last one, the third one is limit 0. So you have to give a proof here why the limit of epsilon, natural log of epsilon is going to be 0. All right, so this tells me, although that is the geometric meaning of this, right? Okay, so you get, what do you get? You get negative 1. So this region is unbounded, right? But it has a finite area, 1. Yeah, it's negative 1. The integral is negative, but its area is going to be negative. Okay? So epsilons here, what you're doing here, you just find the area of this region first. Okay, it's always smaller than 1, and when epsilon approaches 0, and the limit is going to be 1, negative 1. Negative 1, of course, because this is on the x-axis. The area of that region is going to be 1. Okay. Yeah. Before we do the computation, we don't know. sometimes it looks like a very large area region. Now the area will be unbounded. The area will be infinite. Yeah. Right. So this is a good example. And let's look at the next problem. Evaluate the integral from 0 to 1. Yes, 1 of x dx. Okay. Yeah, look at this function. This is a function. It's not defined on the closed interval. Okay. This is defined on only on the open interval from 0 to 1. Okay. And the 1 is yeah, this is not closed interval. So the integral itself is not defined because it's not closed interval. It's not defined on whole interval. Okay. So this integral is we call it improper integral. It is understood to be. Let's use any number. Let's b approaches 1 from negative side, from 0 to b. Okay. Right. Okay, so the antiderivative of x, 1 of x minus 1 is this. Okay, this is actually, the integral should be the negative one because x minus 1 is always negative. Okay, so let's evaluate. B minus 1 minus natural log 0 minus 1. 0 minus 1, this can be 0. Yeah. Right. So we'll get natural log, let's say b 1 minus b first, right? Wait a minute. Yes, that's correct. So when b approaches 1 from negative side, okay, 1 minus b approaches 0 from positive side. Yeah. When b approaches 1 from negative side, it's equivalent to saying 1 minus b approaches 0 from positive. Right. So that means this implies natural log of 1 minus b approaches negative infinity. Right? So this can be negative infinity. So let's take a look at the picture here. Yeah, why this could happen. Okay, y equals 1 of x minus 1. How do you sketch the graph? Let's just shift to the graph of 1 of x. Okay, and that's going to be the graph. Right? When x equals 0, you get a negative 1. Okay, so the geometric mean of this integral will be the negative area of this region. Okay. And it tells us this region has this region is unbounded, but the area of that region is going to be positive infinity. Okay, so the area, right, is going to be positive infinity of that region. Okay. It's hard to tell, before you evaluate it. Okay, so what we are doing here is we just cut. Let's look at the b. Just look at that area. This is always finite. Then you take a limit, and you get the integral from 0 to 1. Okay. So let's take a look at another problem. The integral so this is a function. Now you have the interval here is is from negative infinity to positive infinity, okay? So both sides. How can I define this integral? Well, you can choose an arbitrary point, right? So this integral, by definition, you have to work out both. Okay. Then focus on each of them. Now this time the function is symmetric. So the one on the left is equivalent to, it's the same as the one on the right hand. Okay. So you have to evaluate each of them. And this is going to be, and here's a negative infinity from B to, and this will be the positive infinity from 0 to B. Okay. All right, so still, do you remember this antiderivative 1 plus, 1 over 1 plus x squared? Arctangent, right? So arctangent. So arctangent x from B to 0. And here, arctangent x from 0 to B. Okay. So what do we get here is this is negative arctangent B minus 0, because when x is 0, arctangent is 0, 0. Okay, and here B approaches positive infinity and arctangent B minus 0. Okay, so the limit of arctangent B when B approaches negative infinity is going to be negative pi over 2. Negative pi over 2 or positive pi over 2? Yeah, I have to exchange the order here. 0 minus that instead of, yeah, because B is above it. And 0 minus arctangent B. So that would be positive. Yeah. That would be 0 minus that. Minus negative pi over 2. So it's actually positive. The first part is positive with pi over 2. The second part is the limit of arctangent B would be approaching infinity. It's also pi over 2. So the answer would be pi. So this is another way we get a pi, and the pi shows up. It looks like funny, right? It's nothing to do with the trigonometric geometry. We're only talking about the integral, see, when x equals this to 1, it goes like that. This is the graph. So y equals 1. Okay? And it's a symmetric even function. And it surprised to me the area of that region is going to be the area is going to be pi, which is the area of the circle, unit circle. It's hard to believe, right? And when you look at this kind of region, okay, 1 over 1 plus x squared, it's nothing to do with a circle, it's just a function, right? And you evaluate the integral, and then you take the limit, okay? And you find out the area of that region, and boundary region is going to be pi, which is the exact of the area of the unit or unit disk. For example, let me draw the unit. So this is already 1, right? So it looks like that. Okay, this is this. Okay, so the area. Oops, what is that color? Oh, so red and the. All right. They're mixed up would give me different black colors. That's funny. Okay. That's okay. All right. That's interesting. All right. So the area of the region under this graph, 1 over 1 plus x squared, is equal to the area of this unit disk. Okay. Now, our next topic is about the comparison. Sometimes we are not able to evaluate the integral. We still want to know whether this integral exists. Okay, so here's the definition. Okay, here's definition. Let f(x) be a function defined on an open interval. This can be defined similarly for the function defined on bounded interval, but one endpoint the function is not defined. Okay, we say this is a convergent if the limit exists. Okay. Is finite. Okay, not only exists, it's finite. Okay, and then similarly, when this could be a bounded interval, but one side of the function is not defined. Okay, so similar. So for if the function is continuous, okay, so let's say assume that f(x) is continuous and non-negative, that's enough. Could be 0 somewhere. Non-negative on a closed interval on an open bound interval. Okay, then you will see that it's because it's continuous. The function, this one, this always exists, right? Yeah, because it's continuous function. This one increasing is increasing as b goes to infinity. Why? Because when b getting larger, you get more and more area when there's a graph. So this is guaranteed. So it's increasing. You only have two possibilities. Either the limit always exists. Either finite or infinite. So this implies you only have two cases, either infinity or finite. Finite means the limit exists, right? When you say the limit exists. So I don't need to write this here. So there's only two possibilities. This is what we say convergent. And here we say the integral is divergent because the limit is infinite. Yeah. When b increases, this integral, the value of this integral depends on b, right? The value of integral from a to b. So when b increases, you get more area, more area. So that's why it's increasing. Then it can be finite or infinite. If it's finite, and then this we say it's convergent. Now in general, okay, here's a note. Okay, suppose you have a ht, okay, and this one is increasing as t increases, okay, as t increases. Then you only have See, this is a picture, right? Increases to infinity, right? So it's going up, right? It's only go up. So this could be possibly approaches a finite number. Okay, but the limit exists. Okay, so then the limit, you only have two possibilities: either finite or infinite. Yeah. If infinite, it means in the generalized sense, the limit still exists. Okay, it's not like as a function, jump, does not approach some number, right? Jump. So this is this is only two possibilities here. All right. But, as I said, that sometimes we are not able to evaluate the integral. We still want to know whether the integral exists or whether it's convergent. So my question is this integral convergent or not? Okay? Because you are not able to evaluate this integral. You cannot. Okay? Yeah, this is our question. How do you prove that? Okay, you have to prove this is a convergent. So we have the following. We just want to prove this is fine, right? The integral is fine. I know this one increases as b goes to infinity. But I'm not sure this has an upper bound. If it has an upper bound, then the limit is finite and the integral is convergent. Okay? So how do you do that? How do you prove that? Let's look at this. Negative x squared is going to be that, right? And I think I can change it to e to the x. The reason is, right? The reason is, this is just e to the negative x. The reason is negative x squared is smaller than negative x for x greater than 1, right? This 2 as comparison. Okay. Okay, so but then e to the negative x is easy to handle. Okay, so e to the negative x is going to be less than, right? Then I can evaluate this integral. So the antiderivative is e to the x from 1 to b, and that is going to be, so it's going to be, and clearly this goes to, this has an upper bound, okay? This approaches e to the negative b as b approaches infinity. So this has an upper bound, and the upper bound is finite. Okay, so that implies which is going to be that. Okay, it has upper bound. So definitely it's increasing, but it has upper bound. That means it has a limit. So this implies it's convergent. It only have two cases. Either convergent is convergent to finite number, or it's infinite, right? Now it's convergent. Okay. So this is an idea we're going to use to prove if it's convergent. Prove something convergent. Okay, so proof is not easy. You have to find something, compare with that. Okay. So, but we got an idea how do we compare. So here's the thing. Comparison thing. Okay. We assume that f and g are continuous. on the interval from A to infinity, okay? And right. I also know that yeah, let's try this. Right, for x greater than 8. Okay. Then we have this. All right, that means if the one on the right-hand side is finite, then the other one is finite. Okay, so this is important to know that. Okay, so so comments, right? So if this is a convergent, that means finite, then the other one is also finite. But the idea is already explained in the example. All right, so let's look at more complicated problems trying to prove something is convergent. All right, so that's the problem. Let's look at this problem. It's 1 plus sine x, right? And the square x dx. Yeah, let's put a square here. That's problem number 50. Right? I look at the numerator. The numerator is always between 1 and 2, right? This numerator, yeah, make some observations. 1 plus sine square x is always greater than 1, less than equal to 2. Right? Another observation is that this is going to be divergent because p is going to be between p is 1/2. So this is divergent. Right? P equals negative 1/2, which is less than. Yeah, we know that. We already did a computation. Okay. It's the integral for 1 over x to the power p, and that is going to be infinite. Okay, we want to compare our function with this. Now, our integral must be infinite. In order to prove the infinite, this should be the integral of this simple should be on the left-hand side, right? Yeah. So how can I do that? I think I'm going to use this part. Okay. So the integral because 1 plus square sine square is greater than or equal 1. Right? And this side is the infinite, right? Then that pushes the other side. Okay. So this implies all right. Cool. And yeah, let's do problem number 54. It's integral from 0 to pi. Yeah, can you do this? Okay, determine whether or not this integral is convergent. You cannot evaluate this integral. Okay. All right, so let's do it. Okay, I'm going to make a simple analysis. Okay, look at this function. I think the only trouble point is 0. Okay, look, the function is not defined. Yeah, this function is defined only on the interval from 0, but not including 0. Okay, on this, right? So the limit, yeah, so the integral is going to be the limit epsilon approaches 0 from positive side. Okay, and we're not able to evaluate this integral, so we have to use a comparison theorem. I think the difficult part is sine x, but we know that sine x over x is about to 1, right? That's x. So you can think about replace x. Okay, so this implies sine square x over square x is about x squared over square x, okay, which is x to the 1 2 over 2. So clearly this approaches 0. So although the function is not defined, but I'm pretty sure the function is going to be has a limit. Okay, so think about this graph. This tells us a limit, tells the area, right? Although the function is not defined at the end point. Okay, here's a pi. But I know that the limit as x approaches 0, it's going to be just 1. It's going to be 0, actually, 0. So the graph, the function is not defined at the origin, but this could be some graph looks like that. Okay, so if you just look at this geometry picture, the area is finite, right? Yeah, okay. It's bounded region. It's not unbounded. Okay, it's bounded region. Maybe you can later on assign a value to the function at that point. It become a continuous function. Okay, so this indicates you can even make this will be sine square x if x is between 0 less than pi and 0 if x equals 0, right? And then you can say that h is continuous on the whole interval. Okay? Yeah, this is a side remark. We don't need that, but I'm pretty sure the function is continuous this time. The integral is convergent. Okay. Yeah. What I need is in the following encoding. Okay. There are many ways to do the problem. Okay. I know this is going to be less than x and greater than 0 for x. Okay. For x greater than 0. Okay. So sine square x or square x is less than x squared square x, which is x to the 3 over 2. Okay. Oh, it's always there. So that indicates right. So if you pass the limit, if you let epsilon equal to 0 from positive side, so you will get it's controlled by this, right? So this is going to be finite number, okay? This is a finite number, right? No worry, don't worry about it, right? So that implies this is a limit. Yeah, this implies it is converging. Okay. I don't know the value, but I can have an estimate at least from here. If I can estimate the function, I can estimate the integral. At least I know. Yeah, the function is non-positive and non-negative. So this integral, this improper integral, it's not from infinity to pi. Yeah, from 0 to pi, either finite or infinite. So we now prove that it cannot be infinite, so it must be finite. Okay. So you have to find the function to compare with that. That's the difficult part. Okay. And then, yeah, then you can, yeah, once you function compare with that, then you actually also can estimate the integral. All right, we go back to the problems we just what? Yeah, we should look at some other more problems. Let's do problem number 36. Right. We have to say whether this integral is convergent or divergent. So take a look at this function. Right? So this is going to be x minus 2x plus 1. We check it out. Right? Now, this is, it is defined on the following interval. It's from 0, because when it's right, and the 2, and from 2 to 4. Right? So when x equals 2 is undefined. Okay, how can I give a definition of this integral? You cannot say the function undefined at one point inside the closed interval, then the function is not defined. This is going to be defined to be it's going to be the integral from 0 to 2. This becomes improper integral from 2 to 4. Okay. All right, now, so you have to look at the both, right? And how can we do this problem? X plus 1 is never be 0 over this interval. X minus 2 is a factor. You have to pay attention. Right? So this is supposed to be the limit as b approaches 2 from negative side. And here's x minus 2, x plus 1 dx. And this is going to be the limit from positive side. Okay, so you have to evaluate, you have to find the antiderivative of this function in order to solve it. And how do you find the antiderivative of the function? You have to decompose it. Okay. You will get, let's say them together, x plus 1 minus x minus 2, you get 3 in the numerator. So I have to divide by 3. Right? So this is and then the antiderivative of this function is going to be 1/3 minus, so this is the antiderivative. Okay, you can put them together as one number. Okay. So this is going to be 1/3. Okay. So once you get an antiderivative, that's then let's look at the above three integrals. Okay. Right, so this is going to be 1/3 in h log, and we evaluate the 2 points. That's b minus 2, b plus 1, minus, when x equals 0, it's again negative 2 over 1, so it's negative, it's negative 2, so it's positive 2 right now. Okay, just don't worry about the second number, but the first number. H log of b minus 2, when b approaches 2, the numerator approaches 0. So H log approaches negative infinity. So this will be as b approaches 2 from the negative side. Okay. And similarly, you will get right. So you already know the antiderivative of the function. So let's do this. 4 minus 2, 4 plus 1, minus 1/3, natural log of b minus 2, b plus 1. All right, let's look at this one. When b approaches 2 from positive side. Well, the first term is 2 over 5, no problem. The second term, we have a problem here. When b approaches 2, no matter which side, the numerator approaches 0. So it's going to be negative infinity approaches as b approaches 2 from positive side. So it's going to be still going to be positive infinity, okay? So now you clear that. The one, that's two integrals. The first integral approaches negative infinity. The second integral approaches positive infinity. So yeah, this is going to be negative infinity. This is going to be positive. So you cannot combine them together. So that's why this is a divergent. Yeah. Okay. It is going to be divergent. So this integral is divergent. It's divergent. Yeah, so first of all, you look at the function, okay? And that was the interval for the integral, but the function is not defined everywhere. Could be, it's not defined at one endpoint or even in the middle point like this way. Then you have to divide the, if it's in middle point, somewhere in the middle, then you have to divide the integral into two integrals. And you focus on each of them. Okay? Then if it's defined, it's not defined at the end point, then you just one single integral, you take the limit. Okay, so that's what we do the problem. I'm going to just do one more. There's one more problem. Okay, for example, like this. Okay, now well, let's recall what is it in that what is the antiderivative of this function. I think that this is going to be arc sine x, right? When you differentiate, you get 1 over square root of 1 minus x squared. Right? So we use that, and then you also look at the function square root of 1 minus x squared. This function is defined only on the interval from 0 to 1, and the 1 is not included. Because when the x squared equals 1, then the numerator denominator is 0. Okay. So the antiderivative, this improper integral have to be the limit. Okay, and that is going to be that's going to be arc sine x. Okay, so arc sine 1. What is arc sine 1? Arc sine 1 is going to be pi. Now pi over 2. Okay. Yeah, this is priority. Now, if let's go back to this problem, right? So yeah, this last problem is interesting. And evaluate integral from -2 to 3. All right. All right, so look at this function. If you don't pay attention, yeah, let's do the long way, okay? X to the -4 dx. So the antiderivative would be -4 plus 1 is -3, right? Then you evaluate the 3 and the point. Then you will get -1/3, 3 to the -3, okay? Minus okay, let's simplify a little bit. Negative, negative, negative becomes still negative. Okay. You have to do 3 times 2, 2. I think this is going to be a negative number. Why it's going to be a negative number? You take, yeah, every term is negative, so I don't even do that, right? So something's wrong with that because x to the -4th is positive. Okay, this function, okay, is positive, right? Now how can you the integral is negative? Okay, because the function is not defined, so you cannot apply the calculus, the fundamental theory of calculus to this problem. Okay, the function, this is the wrong way. Okay, so the reason is the function, and here's -2, here's 3. The function is not defined at this point. Okay, the graph looks like that. Okay, so from the graph, it cannot be negative, right? The geometric meaning of this this graph. So this is going to be supposed to be the area, right? And y equals 1 over x to the 4th. So cannot be negative number. So something's wrong with that. That means, okay, it is wrong just because we did not, yeah, we apply the fundamental theory of calculus to this function, but we forgot the assumptions for that. And the function must be defined on closed interval, and if it has an antiderivative, then use the antiderivative function to evaluate the integral. So what we're going to do here, you have to separate the integral into 2 parts. Right? It's -2 to 0 plus from 0 to 3. Right? And you can show that each of them is going to be infinite. Why it's infinite? Think about it, okay? Just take the limit. And yeah, take the limit. So this is going to be -2. From 0, from negative side, b. And you can show that, okay? Just take a limit and x to the -4, yeah, -3. Yeah, this is obvious. It's easy to do that. Okay. All right, so let's stop here today.